Hi, welcome to Weighing a Bunch of Objects, example of the Central Limit Theorem. Okay, so in this video we're going to do the following. We're going to look at an example of weighing a bunch of objects individually on a scale. And we're going to pay attention to the measurement errors on the sum and average of the objects' masses. And finally, we're going to see behavior that is an example of the Central Limit Theorem. Okay, so first let's talk about what you'll need for this video. So this video assumes you know what the standard deviation of a distribution is. If you'd like more information on that topic, you can see the video Mean, Median, Mode, Variance, and Standard Deviation available on this channel. It will also be useful for you to know what a Gaussian distribution is in this video. If you'd like more information on that, you can check out the video Why the Gaussian or Normal Distribution is Important. Okay, so let's outline our scenario. Let's say we've got a bunch of objects. We'll weigh each of these objects one at a time on a scale to determine each of their masses. Now, this scale rounds off the results to the nearest kilogram. So this means that if we have an object that has a mass of 62.9 kilograms, the scale will say 63 kilograms. And if we have an object with a mass of 34.2 kilograms, the scale will say 34 kilograms. Now, this rounding is a source of measurement error. We're going to assume in this example that all other sources of measurement error are small in comparison to this rounding error. So that means that this rounding error is the only source of error that we have to worry about. Okay, so to understand how this rounding is going to affect the measurements, we need to look at the fractional part of the mass of the object that we're weighing. Now, the fractional part is the part that is after the decimal point. So, for example, if the mass of the object is 65.2 kilograms, the fractional part of that is 0.2 kilograms. Now, let's say that the fractional part of the mass is flatly distributed. Here's what that means. So here we're going to simulate 1 million trials where in each trial we randomly choose an object and weigh it. And then we're going to plot the fractional part of its mass. Okay, so we said that the fractional part of the mass was flatly distributed. We can see what that means by looking at the plot at right. So if we look at the number of trials that ended up in each of the bins for the fractional part between 0 and 1, we can see that approximately the same number of trials occurred in each bin. This implies, for example, that 10% of trials have a fractional part between 0.1 and 0.2 kilograms, and 30% have a fractional part between 0.4 and 0.7 kilograms, and so on. Okay, so now let's talk about the measurement errors. So, for example, if the mass of the object that we're weighing is 67.9 kilograms, the scale reading that will be returned is 68 kilograms. In this case, the measurement error is 0.1 kilograms because the reading is 0.1 kilograms above the true value. On the other hand, if we have an object with a mass of 43.2 kilograms, the scale reading will be 43 kilograms, and in this case the measurement error will be negative 0.2 kilograms because the scale reading is 0.2 kilograms less than the true value. Okay, so let's say that we weigh n objects, always one at a time, on this scale in order to determine their masses. and we're interested in looking at the measurement error on two quantities. One, the sum of the n masses, and two, the average of the n masses. And what we want to know is, what is the typical size of these errors? In order to get that, we're going to look at the standard deviation of the error distribution. Okay, so let's start with the case n equals 1. So in this case, we're just weighing a single object. Again, we're going to do 1 million trials. So we can see from the plot that the measurement error is again flatly distributed, and it goes between minus 0.5 kilograms and plus 0.5 kilograms. Now, we're going to get the standard deviation, which we call sigma, of this distribution numerically. It turns out that the statistical uncertainties in sigma will show up in the fourth significant figure. So in order to avoid confusion, we're just going to quote sigma to 3 significant figures. So when we numerically calculate the standard deviation sigma of the measurement error shown in this plot, we get that sigma is equal to 0.289 kilogram. And in this case, because it's a simple distribution, we could alternatively do an analytic calculation. If we did that, we would get that sigma is equal to 1 over 2 square root of 3 kilogram, which is approximately equal to 0.289 kilogram. Okay, next, let's look at the case n equals 2. So now, for each trial that we do, we're going to weigh 2 objects individually, one at a time, and then we're going to add the 2 masses together in order to get the mass sum. Again, we do 1 million trials, and then we plot the measurement error of the sum of the 2 masses in the plot at right. We can see that here in the n equals 2 case that the error distribution is strongly peaked in the middle, unlike the n equals 1 distribution, which was flat. We can understand how that happens using the following logic. So in order for the total error to be near plus or minus 1 kilogram, both of the errors on the individual objects would have to be large in magnitude, and the 2 errors would have to have the same sign. So in order to have a total error near minus 1 kilogram, you would have to have 2 errors that are both near minus 0.5 kilogram. On the other hand, in order for the total error to be near 0, both of the errors must be of similar magnitude and opposite in sign, but they don't both have to be small or large. They can actually be over a large range. So for that reason, there ends up being a lot more trials that end up with errors near 0 than near plus or minus 1 kilogram. Okay, so when we actually calculate the standard deviation of this distribution, we get sigma equal to 0.408. In this case, it's also not so hard to do an analytical calculation, and if you do, you get that sigma is equal to 1 over the square root of 6, which is about equal to 0.408. Okay, now let's move on to n equals 100. In this case, we calculate sigma, again numerically, and get 2.89 kilogram. Now, that number might seem a little bit familiar. It is in fact 10 times our result for the n equals 1 case, where sigma equaled 0.289 kilogram. You might also notice that the shape of this distribution looks very Gaussian. In fact, let's plot a Gaussian in red on top of it. And we can see that the curve fits the shape of the distribution really well. Now, in fact, this is a manifestation of something called the Central Limit Theorem. It says that the distribution approaches a Gaussian distribution as n becomes large. Okay, so let's look at a couple more large values of n. Here we've plotted the error distribution for n equals 400. And in this case, when we numerically calculate sigma, the standard deviation, we get 5.78 kilograms. And lastly, let's look at the case where n equals 900. Here, we get that the standard deviation of the error, sigma, equals 8.66 kilograms. Okay, so let's consolidate all of those results. Here we have a table where for each value of n, we give sigma in kilograms, and we give sigma in kilograms divided by the square root of n. And the important thing to see here is that sigma divided by the square root of n is a constant. In all cases, we get 0.289 kilograms. So this tells us that sigma is proportional to the square root of n. So this result that sigma is proportional to the square root of n is exact for any integer greater than or equal to 0. We're not going to actually show that here, but if you want to understand how that comes about, the logic is very similar to that we used to calculate the standard deviation given in the video mean and standard deviation of the binomial distribution. So you can check that out. Okay, so let's talk about what we've just seen. So we see that the typical size of the error on the sum of the n measurements goes as the square root of n. But if instead we wanted the average mass of the n objects, we would divide that sum by n. And this means that for the average mass, the typical size of the error would actually go as 1 over the square root of n. So this means that if you want smaller errors on the average value, then you should do more measurements, as long as those measurements are independent of each other. Okay, additionally, we started with a distribution for the error on the measurement of a single object. And that distribution was flat between plus and minus 0.5 kilograms. From this, we simulated the error on the sum of the masses of n objects, and we saw that as n got large, the distribution of the error approached a Gaussian. So this Gaussian behavior is predicted by the Central Limit Theorem. It doesn't depend on the fact that our initial error distribution was flat. We could have started with a distribution of some other shape, say a Gaussian or a triangle, that has a finite standard deviation. As long as that same shape held for all n objects, the Central Limit Theorem says that as n goes to infinity, the error on the sum of the object masses would approach a Gaussian. So in case you're wondering, there wasn't something special about our starting error distribution shape. Okay, so let's summarize what we've seen. So here we looked at the error on the sum and the average of the measured masses of n objects. We saw that the typical size of the error on the sum goes as the square root of n, and that means that the error on the average thus goes as 1 over the square root of n. So this demonstrates the utility in getting large sample sizes for measurements. We also saw that the error distribution for the sum of the masses approaches a Gaussian as n goes to infinity. And this behavior is an example of the behavior of the Central Limit Theorem.